Power in a circuit refers to the amount of energy that can be converted from one form to another. Looking at RLC circuits, we find that there are three types of power present in that RLC circuit. Those are my three legs of my power factor triangle. The first is my true power. Now, looking at all the phasor diagrams that we've done, we found that the resistor is the only component that has its voltage and current in phase with each other. As a result, again, my reference would be over here. My true power is equal to I squared times R. As a pure resistor, it does no energy conversion other than converting it into heat. My apparent power, S, is equal to the supply voltage multiplied by the supply current. In all the cases we've looked at so far, that value cannot be a true value because of the phase shift that occurs between the voltage and the current. As a result, my apparent power, S, is measured in VA, or volt amperes. True power is measured in watts. The vertical, we will recall, occurs as a result of the inductor and the capacitor. Now the inductor and the capacitor gets that phase shifting ability because of its ability to store a charge. So when we calculate the reactive power, Sx, we find that Sx is equal to V times I multiplied by sine theta, where theta would be the angle between the true power and the apparent power. The reactive power is measured in VAR. The power factor refers to the ratio between the amount of power that has been converted with reference to the amount of power that has been supplied to the circuit. So, power factor is equal to true power divided by apparent power. Now, applying all the mathematical rules by substituting, instead of power, substituting I squared times R, and instead of S, substituting V times I. If we go through all of that details and substitutions and cancellations, we will determine that the power factor for a series circuit can equal R over Z, or it can equal VR over total supply voltage for series circuits. For parallel circuits, we will determine that the power factor is equal to the resistive current divided by the total current. Now, thinking back to mathematical aspects, the phase angle in other words, the determination of theta over there, if we apply trigonometry, we will find that in a series circuit, my phase angle works out to be cos theta is equal to R over Z, or cos theta equals VR over V total. So we can see the formulas for power factor is the same as the formulas for the phase angle. When it comes to parallel, cos theta is equal to IR, or resistor current, divided by total current. Applications are specific in the fields of communication, where we use the inductor, the capacitor and the resistor to generate a frequency at which communication takes place via radio waves. Second application is for power factor correction. As you learned in grade 10 and 11, when current flows into a dwelling, that is when the user ends up paying. So if we have a circuit whereby the inductor and the capacitor, or the inductance and the capacitance in the circuit are in harmony, thereby we will find a situation where the inductor and the capacitor is supplying current to the internal circuit, and therefore we're not drawing current from the supply, or we're drawing a lot less current from the supply. So as a result, power factor correction, we have the inductor and the capacitor in harmony, and as a result we are not using the supply's current, but we're using the internal current that was stored in the inductor and the capacitor. So that's power factor correction, and it also leads to energy saving. Whereby we end up using less power from the supply.